Okay, so we probably found that in the chat. That's something I haven't finished writing in the previous case, in the sort of abstract example. I was building my family of independent vectors, and I had begun with V1. I wondered, should I ask V2? Well, then the answer was no, because the V2 we were considering here was collinear to V1. Then the thing is that we should add the V3 because it's independent, but not the V4, so that our basis in that case would have been done by just the V1 and the V3, okay, and so that the column space of A was reducible to the span of V1 and V3. Okay, very similarly, in that previous example, well, in the next example, that one, we can say that a basis of the column space will be the vectors 1, 2, 3, and 4, 5, 6. Okay, and so that the column space of A is spanned by those two vectors. Okay, so that's one way to write things once you have a basis. Okay, so that means anything, I will be able to reach anything as long as it's linear combinations of those two vectors. Okay, this being said, well, actually, you know the R matrix already. Well, if you've read what comes next in the lecture notes, you know the R matrix. Look at this. It has ones like this here. We have a 0 above that one, and we have things that are other coefficients like this here, which are, well, not 0. What does that look like? Well, actually, this is the row reduced echelon form of A, the one you get when you perform the Gauss-Jordan algorithm until the end. Okay, when you perform the Gaussian elimination, and if ever your matrix is invertible, you will end with the identity, but if ever your matrix is not invertible, you will end in a reduced row echelon form. So let me remind you what exactly we mean by this. So it should be a matrix, okay, also called row canonical form. So it's in row echelon form. So you see it only has rows with one leading coefficient. Okay. Below that leading coefficient, we have zeros. Second row, we have one leading coefficient before we have zeros. Above, we have zeros. And actually, in that case, we could, well, the reduced row echelon form that we would get would have a full row of 0 in the end, but, well, it's just the same if we get rid of that, and that's it. And, well, we may have non-zero coefficients above non-pivot values, and that's it. Okay, so it's in row echelon form, and every leading coefficient is 1, so it has been normalized. Okay, not like before when we didn't normalize anything, and the product of the pivots would be equal to the determinant. Here we have 1. Okay, only ones, and it's the only non-zero entry on its column, meaning above and below we should get zeros. Okay, just like here, just like in the previous example here, that one, we have the pivots, okay, this one and that one. Above the pivot and below the pivot, we get zeros here and here, and that's it. Okay, all right. So, what are the implications of this? Well, mostly that in order to obtain the CR decomposition, well, as you know that the R corresponds to the reduced row echelon form, well, that's okay. That's the simple one. That's how you get it. So you perform the Gauss-Jordan algorithm until you get the reduced row echelon. This is going to be your R matrix. And then you look at the corresponding pivot columns to make your C matrix. Okay, so another way to work on that previous example would have been, okay, I start with my matrix 1, 2, 3, 4, 5, 6, 3, 3, 3. I do my Gaussian elimination. Do I really need that? Not really, but well, never mind. So that means I've got row 1, row 2, row 3. I'm going to perform keep row 1, make row 2 minus 2 row 1, and row 3 minus 3 row 1. So I get 1, 4, 3, 0, 1, 0, 0. And this one, do it as I'm doing that. Okay, this one I get that my 0, negative 3, 3 minus 6, so that's negative 3, so that's negative 2, 1, 0. And here I've got my zeros, so 3, 6 minus 12, so that's negative 6. 3 minus 9, that's negative 6, and that's negative 3, 0, 1. Okay, and next one in the Gaussian elimination is going to be keep row 1, I keep row 2, then I put row 3 minus 2 row 2, okay, because my second pivot is going to be that one. My first pivot was this one, second pivot is that one. It's just the usual order without trying to be smart. So that's 1, 4, 3, 0, negative 3, negative 3, and I get 0, 0, 0. Okay, I've got my row of zeros. Okay, so well, I don't really need the work on the right matrix, but on anyway, I've begun doing that. So that's negative 3 plus 4, that's 1, 0 minus 2, 1. Okay, next is going to be well, you know, we've got two things left to do. I've got normalization in order to get pivots equal to 1, and I have to get rid of the above pivot stuffs. So this is what we're going to get. Sorry about this. So I should let's get rid of so this is going to be, well, let's sum up. I've got my two pivots, okay, and I should get, well, let's normalize. It's going to be easier to work then, all right? So I'm keeping row 1. I'm doing row 2 divided by negative 3. So it's going 1, 4, 3, 0, 1, 1, okay? And I get 1, 0, 0 minus 2 over negative, so that's 2 over 3 minus 1 over 3, 0, 1, negative 2, 1. And then what should I do? I should, so on here I've got my 0, 0, 0. So then I should make row 1 minus 4 row 2. So that's giving me 1, my 0, 3 minus 4, so that's negative 1. Okay, and I've got 0, 1, 1. Okay, and well, actually the work I'm doing here is not useful. I'm just looking for that row reduced echelon matrix. All right, so and so 1, 0, 0, 1, negative 1, 0. So that's my R matrix, and well, hopefully this is exactly the one we found. So what does it indicate? It indicates that the pivots correspond to that one, and that one. So the first two columns, right? So I'm going to take the pivot columns, so the first and second. So that's just going to be 1, 2, 3, 4, 5, 6. Okay, and I have reconstructed the RNC matrix without wondering whether the columns were really linearly independent or not. Okay, so is much simpler actually to perform, right? So okay, so that's how we can find a basis of the column space, to find a basis of C of A, create the reduced echelon matrix, and create the C matrix using pivot columns. Okay, that's it.